Hello everybody, welcome to the biggest Hello everybody, welcome to the biggest ideas in the universe. I'm your host, Sean Carroll. Today is the third idea we're thinking about. I originally called it force, but as you'll see, I expanded it to be force, energy, and action. Honestly, this is too much for one video. I'm trying to keep the videos short and punchy, but these subjects kind of rolled into each other, so hopefully it will all make sense at the end. But future videos, I'm hoping will be a little bit tinier. More excitingly, I want to announce that we have technological improvements that behind the scenes anyway. So of course, I don't need to wear the red shirt anymore because I figured out my green screen technology a little bit more. Even more important than that, boom! We now have both a landscape format, horizontal format for the writing that I'm doing on the iPad here, and also we have a dark background with white writing, which many people have requested. So it's an experiment, you know. This is actually probably more like what most people do. It's taken me a little while to catch up to what people were doing 10 years ago here, but let me know in the comments whether or not this is working for you. Also, of course, I should have mentioned this more often than I did, but I do a Q&A follow-up video for every one of these. So if you have a question, leave it in the YouTube comments or on the blog. I'll pick out some of the themes in the comments rather than individual comments, and I will tackle them in another video to come a few days after this one. So let me mention why I'm grouping these things together. You know, we talked about how particles move in classical mechanics, and particle, by the way, means a lot of different things, right? Okay, the Earth is a particle by the standards of our videos here today. But you tell me where the particle is, its location, you tell me how fast it's moving, and then using F equals ma, Newton's equation relating force equals mass times acceleration, I can figure out what it's going to do next. But when you think about it, these words are not necessarily created equal, right? I mean, the position of an object, we can see it, we know where it is, that seems very tangible and readily apparent to us. The velocity of an object, well, you know, okay, we can judge when we see something moving how fast it's going, and even the acceleration we can sort of wrap our minds around. But something like force seemed like an invention of human beings, right? Of physicists and natural philosophers who said, let's invent this concept to make our lives a little bit easier. And energy, likewise, right? I mean, Isaac Newton never had anything to do with energy. He never mentioned energy, even though it's a part of classical mechanics as we now think of it. Couldn't you just get rid of these things and talk about positions and velocities or momenta and do it that way? So, well, yes and no is the answer. There are ways of doing that. And so it's an interesting question about what is fundamental, what is real, what do we really need to keep when we're trying to move physics forward. So that's basically the underlying philosophy of today's talk, to think about whether we really need ideas like force and energy, and we'll get to something called the action. Okay, so remember what we might call the Newtonian, Laplacian paradigm. This is what we're working in here. And what I mean by this is not just classical mechanics, a la Isaac Newton. It's in particular this idea of Laplace's circa 1800 that all you need to know are the positions and velocities of everything at one moment of time. And then you can predict exactly what's going to happen in the future and the past. And sometimes, of course, instead of velocity, we use momentum. Because why not? Momentum in Newtonian mechanics is just mass times velocity. Now, it turns out that for certain more advanced purposes, which we're going to get to maybe in the next video, momentum is better to use than velocity, but we'll talk about the difference between them later. For right now, as long as the mass of a particle is fixed, its momentum and velocity are interchangeable. And then we call the set of all positions and momenta being plural for momentum, something called phase space. I don't know why it's called phase space. I know why it's called a space. You know, we think about space as being just a three-dimensional space in which we live. Mathematicians use space to mean any set that has some extra structure on it. So when you were taught set theory as a wee child, you were taught, like, if you have an apple, a pear, and a banana, that's a set of three objects. Mathematicians will say, if I have the real numbers, okay, all the numbers from minus infinity, not only is it a collection of numbers, not only is it a set, but there's different operations defined on it, like adding real numbers together, or subtracting them, things like that, multiplying them. So that structure promotes you just from a set of objects to a mathematical space. So space doesn't mean three-dimensional, it doesn't mean where we live. It's just a collection of objects, often an infinite number of them, with some structure. Phase space is the collection of positions and momentum. So we might actually write it as curly braces xp This is what means all the positions and all the momenta for all the particles in the universe, okay? Some enormous dimensional space. And the Newtonian Laplacian paradigm is telling us that you give me a point in phase space, I'll tell you what's going to happen next, right? So the rules of the game are, you give me, you specify all the positions and all the momenta, some point in this giant phase space, and then I can calculate the forces. So there's a set of forces acting on each particle, and they will depend on the positions and velocities of all the other particles and on nothing else, okay? So that's why this idea of F equals ma is so powerful, that once you're given the positions and momenta of everything, the forces acting on them will be determined by what all those other particles are doing. And it's from that that you can determine what happens next, because, of course, the change in position is given by the velocity, v, and that's already given to you. If you want, it is momentum divided by the mass. And then the change in velocity is given to you by the acceleration, a, which is the force over the mass. So if you know the force, someone's giving you the position, someone's giving you the velocity, then you just chug forward in time, right? And then you can just say what's going to happen next. So I have my setup right now at this one moment using calculus, like we talked about last time. You can chug forward in time, changing both the positions and the velocities using these other quantities. That is the Newtonian Laplacian paradigm for thinking about physics. And by the way, it's not just particles, so not just particles, it can be anything. The Earth, we often idealize as a particle, but it's really big ball, right? It's really a big sphere. There's a lot of atoms in it. There's stresses and strains and pressures and temperatures inside. All of those can still be accommodated within the Newtonian paradigm. If you think about a cube of something, you know, Jello or something like that, some semi-solid thing that can wobble around, then what you can do is take a little cube inside and think of that little tiny cube as a particle. So it'll have some force acting on it, it'll have some mass, it'll have some velocity, etc. It will be acted on by all the other little segments of jelly right around it that are pushing on it, so you can calculate what the forces are, etc. So this Newtonian Laplacian paradigm, I phrased it in terms of particles, but it works for fields, it works for continua, it works for solids and liquids and gases and everything. That's why back before the 1900s came around, we thought that this was the right paradigm for doing physics. People had a difficult time even imagining it would be anything else. All right. It is something else, but we're not going to get that for a few lectures. Okay. What we want to do instead is ask some conceptual questions about this paradigm. In particular, why position and momentum? Why are those the things you need to know? You could imagine going either way. If you imagine other alternative laws of physics, right, you can imagine you just need to know the positions. Maybe you don't need to know the momentum. You could much more easily imagine that you need extra things over and above this. Maybe you need to know the hopes and dreams of the particle, you know, its goal in life. Maybe you need to know its history. Like, was it sad? Did something bad happen to it? Does it have a traumatic past? Did it have daddy issues? Maybe all those things matter. More mathematically, you know, we know that velocity is the derivative with respect to time of position, and we know that acceleration is the derivative with respect to time of velocity. Why don't we have more derivatives that we could count as part of the state of the system? Newton says you don't have anything more than that. You don't need more information than that. But we could imagine needing more information. There is something that we call the jerk. That is really what it's called. I'm not making this up. That's the name for the derivative of the acceleration. And fewer people know this, but you can go further. There's something called the snap, which is the derivative of the jerk. So if you want to think about it, The position is the fundamental thing in Newtonian mechanics. The velocity is the first derivative with respect to time of the position. Acceleration is the derivative of the velocity, so acceleration is the second derivative of position. Jerk is the third derivative of position. Snap is the fourth. You're not going to like this, but there's something called the crackle. That is the derivative of the snap. And there is something called the pop. Sorry. That is the derivative of the crackle. Now, as a matter of fact, I have never heard any person, physicist, mathematician, or anyone else, use the words jerk, snap, crackle, pop in casual conversation or even in technical literature without just snickering at it at the same time. Like, these are not words that we actually use very much, but they exist. You can look them up. They're on Wikipedia. And you might ask, why, when we're defining what is the system that we need to state, what is the information that Laplace's demon needs to know, why is it sufficient to give it position and momentum, not also acceleration, jerk, snap, crackle, pop, etc.? Well, I don't think that there's an answer to that question that is simple and satisfying. Like, at some point, you say to yourself, the laws of physics are what they are. Could you imagine laws of physics where you needed to know the crackle in order to figure out what was going to happen next? Yeah, I imagine you could. I don't see any obstacle to doing it. There's one little loophole there. You might be able to rewrite a version of the laws of physics that did require knowing these higher derivatives of position as just more things going on, but only positions and momenta for those things, those generalized kinds of things. But still, the question remains, like for real objects in the world, for the Earth and for balls rolling down hills and things like that, we seem to just need the position and the momentum. So I'm not going to explain why, I don't have the reason why that's all that you need, but I'm going to think a little bit about what the implications of it are. So I really do think that the search for figuring out why the laws of physics are what they are, rather than something else, needs to be a humble search. You can't insist that there is one deeper explanation. You will always hit rock bottom. Like, you could say, well, these rules, these laws of physics are the simplest, or the most elegant, or the most powerful, or the most geometrically beautiful. So what? Why do we have laws of physics that are geometrically beautiful, etc.? Beauty is in the eye of the beholder, right? If you wrote out Einstein's theory of general relativity, which in its sort of native tongue is one of the most beautiful theories ever invented, but if you wrote it in sort of Newtonian language, it would look incredibly non-beautiful, it would look incredibly ugly. So even if those were true, we wouldn't know why they were true. So at some point you just have to say that's the way it is. But what you can talk about is what it implies, what it means for how we should think about physics, given that we don't know what all the laws are, right? We're trying to do better all the time. So what this means, what the Newtonian Laplacian paradigm means, is the following fact. Imagine that we put you in a rocket ship. Okay, so here's a rocket ship, but it's not firing, okay? So it's just floating out there in space. It's got some fins to control its motion. Here you are in the rocket ship. And someone asks you over the radio, so they didn't give you any windows. You can't look outside in your rocket ship. These are the rules of the game. This is how thought experiments work. So they ask you, the radio comes on and says, where are you? But all of your instruments are down. You're stuck in the rocket ship. You can't see outside. You can't notice anything that's going on outside. Is there anything you can do to figure out where you are? No. The answer is no, not without looking outside. There's no difference in things you can do in the rocket ship between being at one place in the universe and being some other place in the universe. If you tried to do local physics experiments, measuring F equals ma and throwing baseballs around, there's no difference in the answers you would get no matter where you were located. There is, in other words, no preferred position in space. That is a feature of Newtonian mechanics. Likewise, if they asked you, well, how fast are you going? You might think you could do that. You could read the speedometer or whatever, but if you don't have any instruments, if you're not allowed to look outside, if you're just doing experiments and looking at things inside the rocket ship, you can't tell how fast you're going either. I mean, fast with respect to what? If there's another rocket ship going right next to you, it might be moving at zero velocity, even though you're both moving at high velocity with respect to the Earth. With respect to that other rocket ship, you're stationary. So the moral of that is there's no preferred velocity in Newtonian physics either. So by this point, you're thinking, all right, there's no preferred stuff in Newtonian physics, right? But if the person on the intercom said, on the radio, said, how fast are you accelerating? What if maybe you were accelerating, right? What if there was some rocket fuel going out and propelling you in one direction? Could you tell how fast you're accelerating? Sure, you're pushed downward. You're pushed in the direction opposite to the acceleration, because roughly speaking, you want to stay stationary. You're in a rocket ship that's pushed this way, so you feel that push going on you. So there is a preferred acceleration, namely zero acceleration. You can tell whether you are accelerating or not. And this state of not being accelerated, this is called an inertial trajectory, right? These are the trajectories for which momentum is concerned and kinetic energy is concerned, etc. So there's a preferred class of trajectories in classical mechanics. If you want to think of it, if we draw a space-time, right? So space over here, time over here. There's a trajectory where you start at some point and you're moving at constant velocity, namely zero. There you are. You don't know where you are, you don't know how fast you're moving, but that's an inertial trajectory. You're moving at some constant velocity. Here's another trajectory. Someone is moving with respect to you at some non-zero velocity. But from their own point of view, everything looks the same. They're just going there through space. They think that you're moving, you think that they're moving. It's an equivalent symmetric situation. Here's a third one rather. This person is accelerating, and they know it. They are not on an inertial trajectory. So the point of Newtonian mechanics, one of the features, is that there is a set of things called inertial trajectories, and the space of all inertial trajectories turns out to be the same as the space of all initial conditions. It's isomorphic, if you want, in math speak, equal to phase space. You give me a position and a velocity at one moment of time, I will tell you which inertial trajectory you are on. So that's what's going on. That's why acceleration is not needed as part of the specification of the state you're on. Once you know which inertial trajectory you're on, that's it. And if you're not on an inertial trajectory, you just calculate the force and it makes you go. Okay. So this is, these diagrams and these words might be familiar if you know a little bit or even exposed to a little bit about relativity. This kind of thought experiment when you put someone in a rocket ship and you say they don't know how fast they're moving, etc. If you added to these rules the extra feature that the speed of light is constant to everybody, you would get very quickly to special relativity. I didn't mention anything about the speed of light here. In fact, this same basic set of words was talked about by Galileo. So this is often referred to as Galilean relativity. And it is a form of relativity. It's not Einstein's relativity, it's not special relativity or general relativity, it's Galilean relativity. It's this notion that you don't know where you are, you don't know how fast you're moving. Galileo wasn't talking about rocket ships, but he talked about moving at a constant speed and how you wouldn't be able to notice. So Galilean relativity is built deep into the structure of classical mechanics. So with that in mind, let's think a little bit. So that's supposed to be a discussion of why it's just positions and velocities. Again, we can't actually answer that question. We can talk about the meaningfulness of it. The fact that it's just position and velocities is a reflection of this underlying symmetry of the theory, Galilean relativity. We'll get into symmetries again more later in the series of videos. But now let's switch gears a little bit to sort of dig into this a little bit with an example, because I started by talking about force and energy and things like that, and we want to dig into whether or not these ideas are really necessary or are they just useful. After all, for force, we said F equals ma, force equals mass times acceleration. We also said that if you are under the force of gravity, the force is Newton's constant times the mass of the object pulling you times your mass over r squared. So F equals ma and F equals this stuff, so you can just say that the acceleration is Newton's constant times the big heavy mass over r squared. The little m's cancel, right? And the force goes away. So this is the real physical thing that's going on. You're being accelerated by an amount that depends on how big the thing like the sun or the earth is that's pulling on you and how far away you are from it. did we really need to talk about the notion of force at all? And likewise, energy is sort of the same thing. We can talk about it, it seems to be useful, but we don't need to. So, is it real? Is it fundamental? Is it important? Are force and energy really central, or are they just useful? This might be an important thing going forward. So let's get into this by relating force and energy by looking at a simple example. This is sort of a paradigmatic thing to do in physics, a ball rolling on a hill. So this is the position of the ball, x, and this is the height of the ball. So here's the ball, okay, and it has some position and it has some ability to roll up and down. And this is a spherical cow landscape, a spherical cow hill. So there's no friction, no noise, the ball's not going to fall apart or get stuck or anything like that, okay? We're just going to solve the equations. We're not going to solve any equations, but in principle you would just solve Newton's equation to find out what would happen to the ball. So this is the height above ground, h, right? This is the height of the ball there, h for that ball right there. So the height is a function of x. We're not going to think about the ball as leaping into the sky or anything like that. So if you know where it is in x, then you know how high it is above the ground. So if we come across a ball sitting on a hill like that, you know what's going to happen. If the ball is just stationary, if you set it there and let it go, you know it's going to move. It's going to start accelerating. It's not on an inertial trajectory, okay? So clearly there is some force acting on the ball. Let's erase this so I can do a better job of showing you what the force is. There's certainly a gravitational force pulling the ball downward, and the strength of that gravitational force is proportional to the mass of the ball and something called g. G is just the strength of gravity here on Earth. We're here on Earth. We're not on Mars or Jupiter or anything like that, okay? There is also a force that is perpendicular to the surface that the ball is rolling on. So this is called the normal force, Fn for normal. Why is it called the normal force? Not because it's not abnormal, not because it's ordinary. Normal is a fancy math way of saying perpendicular to. So the force that the hill is exerting on the ball is always perpendicular to the actual slope of the hill itself. So if you take gravity, which is always pulling you down, and the normal force, which is always perpendicular to the slope of the hill, they cannot exactly cancel because they're not pointing in opposite directions. There will always be a remnant force going this way, and that will accelerate the ball down. In fact, you can figure out how strong the normal force is by knowing that the ball is not going to fly up into the air or tunnel down into the earth. It will always keep moving on this trajectory, sticking close to the landscape, and so that's how big the magnitude of this normal force has to be. So from the F equals ma point of view, there's a very natural story to tell here. We started with a position, x, we started with a height, we started with zero velocity. We can calculate the force. There's going to be an acceleration, the velocity will change, and the ball will roll down the hill along some trajectory. Good. It's a good way of talking about it. Remember, we mentioned something called the kinetic energy way back in the first idea video. It's the energy of motion. And for those of you who are fans of equations, it's 1/2 mv squared. But when you start, the velocity is 0, so the kinetic energy is exactly 0. There's nothing happening to this little ball. But as it goes, it's accelerating, the velocity is going to change, so the kinetic energy is going to increase with time. So because there is a force acting on this ball, the kinetic energy is not conserved. You will therefore not be surprised to learn that there is an extra part of the energy that adds up with the kinetic energy to make a quantity that is conserved. And that is the, let me shrink you here a little bit so you can see, the potential energy. The potential energy is the energy that just depends on where you are and your intrinsic property. So like your potential energy might be different if you're a charged particle in an electric field than a neutral particle at the same place. But given your properties, all you need to know to figure out the potential energy is your position. So we call it the energy of your location, where you are. And in this particular setup, the potential energy of the ball on the hill is just the mass times that strength of gravity times the height. And the height, of course, is going to depend on where you are. mgh, h of x. Okay? This curve is h of x, the height of the landscape as a function of x. And so the total energy, E total, is kinetic plus potential, and that is conserved. Oops. So what happens as the ball rolls down the hill, it starts with 0 kinetic energy and some potential energy. And the potential energy is converted into kinetic energy. The potential energy is large when h is large, right? It's proportional to h. And it gets smaller as you go downhill. So given this spherical cow setup where there's no friction, by the time you're at the bottom of the hill, you'll have a lot of kinetic energy. In fact, you'll have exactly as much kinetic energy as you used to have potential energy. The difference in potential energy has all converted into kinetic. So it's interesting because we needed to add this extra term to make the energy conserved. I'm not going to derive this, but you can take my word for this. This is actually conserved. And so we can ask, what is the relationship of this energy language, this energy vocabulary, to this force vocabulary? We didn't need to talk about the energy to solve for the entire trajectory of the particle, right? If we just had done Newton's laws, F equals ma, we could have said everything that there was to say. But we get some insight by talking about the energy. So I just gave you a little bit of insight, right? Given that it starts right here, when it's right here, I could figure out what the potential energy would be if the ball were here, and I know that energy is conserved. So once the ball rolls to that point and is now moving along at some velocity, I should draw the velocity this way because that's how it'll be moving, then we can figure out exactly what that velocity is just using energy conservation and the change in potential. All of its potential energy was converted into kinetic energy. So even though, we don't need to invoke the word energy, we can just use forces. To a little extent, the opposite is also true. There are some questions that we can answer without mentioning the word force. We can start up here with a certain potential energy, answer the question, how fast will the ball be rolling when it goes to the bottom of the hill, just using energy conservation. We don't even need to mention the word force. Having said that, of course, it seems like the energy vocabulary is a little bit less powerful because it doesn't give us the entire trajectory, right? It doesn't tell us everything the particle's doing. If you just put the particle there with 0 velocity and you say energy is conserved and that's all you tell me, well, the energy could be conserved if the ball just sits there not moving, right? That's perfectly allowed. 0 kinetic energy, potential energy stays constant, so everything is fine. So there's many more ways for energy to be conserved than there are real honest-to-goodness trajectories of the particle. So it seems like the force language is a little bit more powerful than the energy language when it comes to asking about problems like this. But it turns out, yet again, that there's another relationship that we didn't mention. We can ask, we talked about the force in terms of adding up the force due to gravity and the normal force. But there's another way of thinking about where the force comes from. The force acting on the particle is minus the slope of the potential. So if we give a name to this, usually the letter that is given to this is V of x, is the potential energy. So V equals m times g, the mass of the particle times the strength of gravity times the height above the ground. So minus the slope of the potential, mathematically that's minus the derivative of the potential with respect to the position. Again, if you're not a math person, just don't look at that part, okay? But still, you can see this kind of makes sense. Let me zoom in here. So the slope, this is a point right here where the ball is, where the slope is going upward, right? It's moving upward. The landscape, the height above ground is increasing as x increases. The force is going in exactly the opposite direction. So the force goes down, it's minus the slope. If you were down here, near a point where the slope was essentially 0, there would be no force. And in fact, you could put the ball down there, you could let it go, and it would not move. There's no force on it. So this relationship, the force is minus the slope of the potential energy, gives you a little bit more clue that energy is a little bit more powerful than we thought. Of course, we don't need to use the word energy. We can just talk about the forces. But if you just tell me what the energies are, I could figure out the forces in this particular situation. So maybe there's sort of more information being hidden in the energy than I let on. You might want to ask, can you replace the notion of energy, the notion of force entirely in favor of something that is more energy-like? Before I answer that question, I remember that's one other thing I want to tell you. We have a feeling that objects, that real balls in the real universe will roll down the hill to the bottom and then they will stop. I mean, maybe they'll bounce around a little bit, but then they will settle down to the minimum. They will go down to the valley and settle at the lowest point. Of course, you can understand by now that that's just because the ball is not in a spherical cow universe. The real world is not spherical cow land. There is friction, there is noise, etc. In this slippery world, it would just slide right on by and go up the other side. But still, there's a remnant of that idea. If you think about the forces minus the slope of the potential, if you were to give into the temptation to assign, purpose and meaning to the life of this poor little object that's just obeying the laws of physics, you would say, well, the fact that the force is minus the potential is saying that the ball kind of wants to decrease its potential energy. If you put the ball there stationary, not moving, it wants to move in the direction where the potential is lower. It doesn't really want to do anything. The ball doesn't have any desires or anything like that, but it begins to move in the direction where the potential is lower. Because energy is conserved in the spherical cow world, it won't actually stop. It will keep going. But then once it's passed, once the ball is up here and still moving in this direction, this is the velocity of the ball here, but the force is now acting in the opposite direction because the force is going to want to pull it back to where the potential is at a minimum. So there's some kind of quasi-teleological language sneaking in. What does the ball want to do? What direction does it want to move in? Things want to move in the direction in which their potential energy is less. That's another little bit of insight into the relationship between these concepts. Okay, how far can we go in relating energy and force in this way? We can go very far as long as you're willing to stretch your mind in a little mathier direction, okay? Let me tell you what I mean by that. I want to talk about the space of all trajectories. We already said that a space is just a mathematical way of saying a collection of things with some extra structure. So consider all possible trajectories between, we're not going to think of all the trajectories of everything in the universe. We want between 2 points that we specify at 2 times. In other words, imagine once again space, time. We're imagining that we have some location x0 at time t0. I don't know why we just don't say 0. We like to say naught in these situations. And then we have some other point here. This is a new location, x1 at time t1. And we say, think about all the ways you could get from there to there. Okay? So you could take...
I've been working on this topic for a while now. It's not something new to me by any means. The topic, oh wait, before I jump into it, did you have like t-shirts and stuff? Okay, so the Austin School does have t-shirts. They are available. Kelsey has them. Yeah. So the front is cool, but the back is better. So that's the front. But the back, I don't know what to make of this, but I just don't know. Anyway, so this is the back. You kind of need to have one of these, I'm pretty sure. We're using it to fundraise for the Austin School, so it goes to a terrible cause. $18. All right, so back to the topic at hand. So one of the things that I've often wondered about is how do these categories come into being? I was actually talking about this earlier, but just as an example, I had a student about a year ago who was black, and by black I don't mean like he was African American. He actually had to put white when he filled out race because he was from North Africa. But I mean, he was black, like his skin was black. When you see him in the street, you're gonna go, look, there's a black guy. You're not gonna go, oh my God, look at that white guy who looks very dark. But when it came time to bubble and race, he had to put in white, right? So like, how the hell did we get that category? Clearly this is a category that's arbitrary at some level. There was a rule made, and then we just take people and we jam them into these categories. And one of the categories that's always struck me as sort of odd was this east-west category that we have. So if you were here on Thursday, I took this on a little bit and I talked about how that category formed in terms, and why it mattered in terms of foreign relations. But I'm going to take this thing even further back and dig into it a little bit deeper, because that's pretty much all this is about. So even though this talk is a brief history of Western civilization, to do that, there has to be an East, right, to compare it to, because you can't really understand what the West is unless you have an other to look at. And then you say, oh, really what the West is not that, right? Usually when you define something by what it is, you really don't know what you're talking about. But when you define it by what it's not, it brings it into light a little bit. So I want to take this thing and look at the very notion of the idea of the word civilization. So we're going to do the East-West divide, but we're also going to do civilization versus non-civilization. Historians have traditionally, I'm going to start with civilization, and historians have traditionally defined civilization as starting with the advent of writing. Now the reason historians have picked writing is it's actually really simple. It's that all a historian really is at the end of the day is a person who does non-fiction literature, right? The difference between the history department and the English department is that the historian is doing non-fiction and the English department is doing fiction. That's the primary difference between the two. Because at the end of the day, all a historian is doing is reading historical texts and maybe trying to put them to memory, and then trying to create a narrative based on what they've read.